Today I'm going to talk about binary to decimal conversions. You know that show, The Price is Right? It's been on television forever. So what's the main rule in The Price is Right? The winner is the closest to the actual retail price without going over.
You had the game room. That was really fun. Brand new car in your showcase. You bid $26,844. Actual price is $26,363. Oh, that was so close. Brianna, trip to Martha's Vineyard, trip to Cayman Islands, trip to Australia in your showcase. You bid $25,000. Actual price. Come on. $24,996. She was over by $4.
If you can follow that rule, you can do binary to decimal conversions. You have to get closest to the number without actually going over. And so I'm not really a math person. I have never been really strong at mathematics. I've figured some things out about it, but I have to think it through. And so I like to do things visually. So I'm going to just kind of show you my visual approach to doing binary to decimal number conversions. First of all, why binary numbers? Probably the most important use of binary in the world today is it's the language that computers speak, right? I remember there was a scene in Star Wars where Uncle Owen was looking at the droids on Tatooine, and he was talking to C-3PO and asking if he could speak binary, and of course C-3PO can speak binary. All digital devices can speak binary. So, but what is binary? Well, binary it's ones and zeros. So basically, it's a number system that has only two numbers in it. Unlike our base 10 system that has 0 through 9 in it, that's what we normally use. And some people say it's because we have 10 fingers, and so we have 10 different digits. And that makes sense to me. But computers, because they're electrical devices, it's easier to have ones and zeros and leave it at that. It can be expressed as a voltage. So if I turn the power on, that's a 1, and if I turn it off, that's a 0. So you send these digital signals that you can represent ones and zeros quite easily. So that's why computers use binary. And so today we're going to talk about how can I convert the number system binary into decimal, which human beings can understand better. Let's talk first about something familiar to everyone. They learn about this probably about first or second grade, and that's powers of 10. Okay, so if I have 10 to the 0th power, that's a 1. And if I have 10 times itself just one time, you get a 10. If you take 10 times itself twice, then you get 100. So forth and so on. 10 to the 3rd power, 10 with 3 or 1 with 3 zeros, or 1,000, so on and so on. So this in powers of 10, the exponent represents the number of zeros after the 1. So 10 to the 50 power is 1 followed by 50 zeros, whatever number that is. All right, so yeah. And then in like first or second grade, we said, okay, these are my ones, these are my tens, these are my hundreds. And so if I write a 5 here, then this is going to be 5 times 10 or 50. So this this would be 50s. And if I have a 4 here, then it's going to be 4 times the 1, or just 4s. And if I put a 2 over here, it's going to be 2 times 100, or 200. And then you add them all up, and you get 254 as a number. So that's the basic idea with powers of 10. And we can do the same thing with powers of 2. Except in base 10, we have characters 0 through 9 to work with. But in powers of 2, or binary, we just have 0 through 1. We have those 2 different numbers, like I said, represented by voltages, and they can be used in a computer. So let's review what the powers of 2 would be then. So 2 to the 0, anything to the 0th power is 1. 2 to the first power is 2. 2 to the second power is 2 times 2, which is 4. 2 to the third power, notice these just double too, so it'd be whatever this one is times 2, or 2 times 2 times 2, which is 8. 2 to the fourth power, 16. 2 to the fifth, 32. 2 to the sixth, 64. You keep doubling it. 2 to the seventh power is 128. And I'm going to stop here for an important reason. Because notice I have 8 different numbers here now. If I count them up, 1, 2, 3, 4, 5, 6, 7, 8. And if we call each one of these digits a bit, or a binary digit, did you know that? A binary digit is the word bit is a contraction of those. A bit is just a binary digit. And so if I have 8 bits, I have something called a byte, or a computer word, basically. So we use 8-bit numbers a lot in the world of computers. Okay, so knowing these powers of 10, you can memorize them if you want to, but for me, it's just easier to remember 2 to the 0 is 1, and then double it, and do that 8 different times. So you get 1, 2, 4, 8, 16, 32, 64, 128. And if you can remember that and write those powers of 2 out like so, then that will help you do the binary to decimal conversion. All right, so let's set that aside for a second, and I'll write them out again. Okay, so all right, so I like to just make myself a chart with these powers of 2 in it, and a lot of times I just write the actual powers of 2. I don't write the number 2 to the 0th and so on. But you can, for this example, I'll do both, just like what I did there. So 1, 2, 4, 8, 16, 32, 64, 128. And I like to make myself a little grid then. Sometimes I hand out worksheets in my class or something like that. But just as a reminder, that's 2 to the 0th, 2 squared, 2 cubed, and so on. Okay, so I've got those powers of 2, and there I've got 8 bits. And then let's say they give you the number, an 8-bit number. Let's see here. What is 1, 0, 0, 1? There's 4, 0, 0, 1, 0. Okay, so there's an 8-bit binary number, and I want to see what that is in decimal. I want to convert that. So I go ahead and I write that in my grid. So, okay, so it starts with a 1, a couple of zeros, a 1, a couple of zeros, a 1, and a 0. All right, so that's my number. And then to take it into decimal, or base 10, like humans are used to reading, you just add up all of the ones. So I've got a 2 and a 16 and 128. If I add all of those up, then I'll get whatever the decimal equivalent of that is. So there's a 10, 16, 4. So this number in base 2 is equal to 146 in base 10. Okay, does that make sense? So that's converting binary to decimal. It's really not that hard when you make yourself a grid with the powers of 2 and you put the number in there and then you add up the bits by their position in there. All right, so but what if you want to go the other way? What if someone gives you a decimal number and they want you to make it into a binary number? All right, so we'll set that one aside. I'll just rewrite my grid, reuse that like this. So instead of writing it all out again, somebody give me a random binary or a decimal number that I want to go into binary. Let's go 205. All right, so that's the number I'm trying to do, and that's in base 10. What would that look like in binary? All right, so this is where the Price is Right analogy comes in. You have to pick the price, pick the binary digit that is closest to the actual price without going over it. And just to prove a point here, let's go ahead and write in 2 to the 8th power is 256. All right, so 256 is larger than 205. That one would have a 0 in it. We wouldn't use it. So we know we can come up with a number that's equal to 205 just with these 8 different bits. All right, so obviously this one's too large, so I know 128 will fit inside of 205. So I put a 1 there. And then what I need to do is I need to subtract that number from my original 205. So let's just do that. 205 minus 128. Like I said, I'm not real good at math here, but 19, okay, 8, and 15 minus 8. 7. Why'd that take so long? Why'd that take so long? I don't know. 9, 8, 7. So 77. If I put a 1 here, I've expressed that 128 now. So we take that out of the picture. I'm left with 77 that I need to express with the remaining numbers. So I look at the next digit. Does 64 fit inside of what is left? Yes, it does. So let's go ahead and mark a 1 inside of that too. We'll represent the 64 in here. So I'll bring that down and subtract that out and see what is left. 7, 6, 5, 4, 3. So 13 is left. All right. Now, does 32 fit in what is left? 13? No. The old Price is Right thing. It goes over. It's too large to fit into the remainder here. So we put a 0 there. 32 is not needed. 16, it's too large to fit into 13. We don't need that either. Looks like we're going to use an 8 to express the 13. All right, so 13 minus 8. So that would be, what is that, 5? 5 and 5 and 3 is 13. Okay. So 5 is what is left. 4 fits inside of 5. So we put a 1 in the 4 spot, and we subtract 4 out, and we're left with 1. So 2 is too large to fit inside of 1, so it gets a 0, and then we finally put a 1 there to come up with the final number. So 11001101 should add up to 205. Like that. So that's the 8-bit binary number equal to 205. So like I said, if you're given a binary number, you add up the ones, and that will give you your number. And if you are given a decimal number, then you just get your powers of 2 out, and you do this subtracting process. You pick the largest one, put a 1 in it, and then find the next number that fits. Put zeros for whichever ones don't fit. And that's the basic process for binary number conversions.